Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at food calorie prediction. Specifically, what we'll do is we'll use nutrient information, so combination of nutrients, just protein, carbohydrate, fat, etc., and use that information for a particular product and see if we can predict how many calories would be in that product. And the video is divided into three parts. The first is where we'll read the data into a data frame. Next, we'll pre-process it, and then we'll fit machine learning models that we have learned so far. Many thanks to USDA Food Data Central for providing this data open source so that we can freely use it. I'll put the links to download the data in the description below, which is this. And this is page for the resources where you can read about what this particular data set is about. Story of food labels and products. So here's what I gather from this. You probably already are familiar with this. So if we have, let's say, a product of sliced apples in a can as shown here, the part where we show the sliced apple, like image of what the product is and its the name of the product or the brand, that's called the principal display area, and that's shown right here. And then next to it is the information, which is the nutrition information or serving, that has information such as grams of fat, grams of protein, carbohydrates, vitamins, etc. And it also has the serving size and the manufacturer's name, etc., below it. So that is the nutrition label. And what we are going to do is we are going to use the information that's provided in that label for a product and use that information to predict how many calories that particular product would have. A combination of those nutrients would have how many calories. And the data for that, after you download the file, zip file, which would be this one. On the side, you can download other files as well. So I've downloaded different versions of the data and looked into it to see what's in there, and finally decided to go with this particular file, which will be the link in description. This has these many CSV files. Some of them are do not fit in the page, so I've cut this off here. And what we are going to do is read the CSV file, not all of them. I've selected just few of them, and then we'll put them in a data frame and then go from there. The download, there's a PDF as well. So the PDF is really helpful because it shows the description of what's in each of those files. Without opening, we can see the description. So the date, let's look at the description first. So when you open the PDF file, you'll see the file name written here, and then these are the columns, names of columns: FDC ID, acquisition date, etc. And then this is what the description is for the each of those columns. So uh, when we are trying to work with this data, immediately you'll start thinking that we can join these tables by selecting the primary ID. For example, FDC ID should be a unique ID for a particular product. So we can join FDC ID with FDC ID in other table, for example, this one. And then we can combine the branded food table with the agriculture acquisition table. So that's how one would proceed. However, there are uh, certain issues with how we need to figure out how to do that, because it what happened is some of the FDC IDs from this table may not be in the other table, or this table would have completely different set of FDC IDs, so you may not be able to join any of the rows from this table with another table. Also, there are in some cases you'll find that the file name uh, or file name that is written here or the column name uh, has sometimes a typo, so you have to check if uh, check for those when you are trying to run these. And additionally, there are other types of IDs, for example this ID, and there is no description for this, so I'm guessing that's the unique ID for the rows in that table only. And so there is certain amount of guesswork involved in this. And if you're working with a data set, you always want to be 100% sure what each column of the data represents. If you're not sure, you want to go talk to the team who gave the data, be 100% sure, and only then proceed on the further analysis. In this case, however, because this is a teaching lesson or tutorial, I'm going to assume several things in it which may not necessarily be correct, but it'll get us through the process of uh, analyzing the data and making the prediction using regressor models. So that's the description file. This you'll need when working with the data. And the CSV file looks like a standard CSV file, which has a comma delimiter, a separator, and the first row has the names of the columns, and then there are several rows in this. And as you can see, there are several null values as well, which would be expected because not all products will have all ingredients, and so not all the information would be common for all the products. So in this part one, we'll get started with getting the data into a data frame. Again, this is the source of the data, which is US Department of Agriculture. This is the link for the file you can download it from. I'll put the link in the description as well. For libraries, these are the libraries I'm using. Um, and here we definitely need the linear model library. And these are the versions for the Scikit-learn and Python. Now also set the options for the data frame, how many columns we can display at a time. So for part one, uh, the first item that I want to mention is we need to find workarounds or find ways to handle certain challenges working with the data. And some of those are there are typos in file names or column names. And so if that's the case, when you are running through a loop, and if you are getting the file name from the file name and trying to see if that matches some other file of another year, and if there is a typo, it's not going to match. Another thing is missing tables. So I'm not sure if the tables are actually missing, but uh, some of the tables for a particular year are not in that particular folder. So maybe if you look in other folders, they could be there, but I couldn't find it for some of those. And then primary IDs do not always match. So if we have a table, and if you're familiar with SQL, you know that if we are trying to join two tables, the one way is to join them on a specific column, which is uh, unique column in the sense that for each row there is a label, and we can join those labels together to combine those two tables. However, in this case, I found that uh, the label, let's say the number FDC ID, does not always match from one table to another table, and there could be several reasons for that. I, I couldn't get into it, but if they do not match, we basically cannot use that those tables. And then there are several NANs, so there are several zeros, NANs, and that's expected. Anytime you're working with real world data, this is kind of expected that there is going to be a ton of missing information in there. Then the description of each variable. There is a PDF file in which we can read the description. However, while working with the data, you'll still get some questions as to why this is the case, or how this how this was created to make a particular to work on that data. And so I found that that information, it's probably somewhere on the side, but I couldn't get to it. And uh, the reason why I'm talking about it here is, if you are working with a data set, you want to be absolutely sure what each of those columns represent. And here I'm not. So there's fair bit of guesswork, but it should do it should work for what we are trying to do here, which is practice working on project to predict values using regression. So those are some of the topics. And then, as usual, we'll first set the path to the data folder. And in this case, I'm setting it to my desktop. So users, then I have desktop, food, and the name of the file, food data central underscore CSV underscore 2020 dash 10 dash 2030. So that's the path. Now what we need to do next is read all the files. Read all the files and then put them in a dictionary. So we'll initialize the dictionary, read each file, and put the entire file into the dictionary. So it will be a dictionary of data frames, and that's a very convenient to handle all the PDF, all the CSV files. And then from the keys for the dictionary, we can use it to open any data frame. So let's say data is our dictionary, which is initialized by open close parenthesis, and then use for root and then dirs files in os.walk, and here you specify the path. So this is going to walk through the, so we can print this. So let's copy this, and if we print this, we see that we get, okay, let me put the new line characters there, so you can separate those out. And as you can see, that's the root directory. That's the, there's no directory in there. And then these are the files, so each of these files. So talking about typo, you'll see that one that I noticed was this one. So here this is correct, but in some files this I is missing in acquisition. Okay, so we have that. Now we can go ahead and use, so we have to read this list that's in there, which is stored in the files variable. So we'll loop over that. So for file in files, file name is equal to file dot split, and we are going to split on dot, and because this also has a PDF, we need to make sure that we don't open the PDF file. And to do that, we can check if the extension of the file that we are reading is a CSV file. So we'll get the extension here. We get the file name, and then we get the extension. So file dot split, again dot there, and then we get the extension. Now if we see that the extension is equal to CSV, then we are good to proceed. So we say data file name is equal to pd.read underscore CSV and os.path the join root file. So that way we are reading the file as a CSV file and then putting it in the dictionary where the key is file name. So this would be the key for that particular data frame. So we can access it later on. And then file name is equal to uh, we don't yeah that should work. And then we run this, and after this is done we can look at the keys. So if we type data.keys, oh sorry, should be mm, okay, the parentheses. So these are the keys. Now let's say if you want to pull this data frame out from there, or you type it data and then put that in there, and that's our data frame. So first part is done. We got the data from the CSV files into the data frame. We'll take a short break and come back and then do the processing in part 2. Welcome back to part 2. In previous part, in part 1, we looked at how we can bring the data in this data frame. Now, after this, what I tried to do, at least what my goal was to bring all of these files into a single data frame using the uh, primary IDs such as the FDC ID and other IDs that are in this particular data frames. However, I quickly ran into problem where these IDs did not match for most of the rows, and so ended up working with only a small subset of the CSV files from this entire data set. And what I'll encourage you to do is use the kind of using this tutorial as a sample so that you can explore other data in this particular data set on your own and see if you can use that not only for regression but also for classification. So you can create the data that you find interesting, create a data set from these files and then put them together, uh, run it through classifiers and see how the results turn out. So here we are going to look at branded food. So this is part 2. Part 2 and no particular reason I've chosen this, just that those files worked and that was the first file I picked. Now for the data has several uh, NANs and zeros. So I'm going to first create a function drop underscore NAN underscore dupes. So after joining two data frames, uh, sometimes there is chance that you may be creating duplicate rows, especially in a situation where let's say there are 10 columns and after joining you have 20 columns. However, there is only one column that is different in the new table that you've joined. So all the values in each of those rows could be same except that one column. And so if you happen to delete that one column for some reason, then you have duplicate rows in there. So this function will take care of that and remove those. So dfx is equal to dfx dot drop duplicates. So we are first going to drop if there are any duplicate values, and then we are going to check the number of NaNs or NaN values in there, and if they are greater than certain threshold, we are going to delete those columns. So for call in dfx dot columns sum nan, so total number of nans in a particular column. dfx call dot is na dot sum. So this gives us the total, and then we check that using the if condition sum underscore nan. If that is greater than or equal to a set threshold, in this video I'm using a 50,000 threshold. So if there are more than 50,000 values that are nans, we just get rid of that particular column. dfx dot drop, and then we have, sorry, this shouldn't be in quotes, call, and we have axis is equal to 1, and then we want to return dfx. So that's the function. And again, the path, we've already set the path above, so we are good there. Now for reading the data, we have already done the part where we uh, write the data to the data dictionary, which is up there. Now it's time for us to pull the data, merge it, and create a new data frame. So branded food. So this, the data pertains relates to branded food, and that's why the heading df is equal to. So we'll first look at data food underscore nutrient, this data frame. So let me put a head there. So here we have ID, FDIC ID, FDC ID, nutrition ID, and then we have these table columns. Out of these, so as you can see, these are NANs, and what I ended up doing is we drop all these columns right here. So the only column of interest is the amount and the FDC ID, and maybe we'll use these IDs for joining, but these columns we end up dropping later on. Then after this, there's another table that we'll look at is nutrient, and the nutrient table again has the ID, has the name, and the unit for. So let's say if this is 35, it could be 35 grams of protein, then it would relate to this column. And again, these are the numbers if you want to join to other columns, and so on. So let me show you what we are trying to get to. So this is the site, uh, food central, food data central, and within this site, if you search for a FDC ID here, you can get an output. And so this is the output right here. We have the FDC ID right here, and this is what we are trying to get at. What we are trying to do is we are going to put this information of nutrients in a data frame, and then predict based on, let's say, fiber total dietary value, soluble fiber, ash, protein, water. Using this, we are going to predict the energy, that is in this case 370. So can we do that? And if we can, how can we improve the accuracy and so on? So to get there, these are the data frames that we'll use. And then the next data frame is data branded underscore food. So in this, you can see there's again the FDC ID is there. This is the UPC code, serving size. We may not be using all this information, but it's there. So you have modified date, available date, etc., etc. So there's ton of information if you want to practice. There's a lot of stuff in here that you can ask questions and then try to find an answer. So let's get started now. To delete these. So first we'll use the nutrients. So why, let's keep those open. Food underscore nutrient dot head, and let's put 2, and then data nutrient, and then dot head 2. Okay, so we are going to join food underscore nutrient and dot merge. We are going to join this with data based on the ID. And that's another thing. So when working with this data, this you have to learn. This is how I start working with new data, kind of trying to learn what each of those columns are and doing some trial error. And this particular data set, we have to join the nutrient ID with this ID, and that's how we can get those aligned. So here I'm going to use data nutrient and left on. So left is our food nutrient data frame, so we'll use the nutrient ID. You would think that this ID would match on this ID because the column names are the same, but that's not the case. And then right on ID, and then want to specify how, so that's using inner join. So df.head, and now we can go ahead and look at the join data frame. It should have all the columns that we have right here. So as you can see, this is a nice data frame. And because the two columns ID, now both the data frames have ID column, it has renamed it as ID underscore X for the left table and ID underscore Y for the right table. And now we have the nutrient info ID and the amount. So we'll keep going. And while we are doing that, why don't we print the shape of the data frame as we go? So that's the, and so we have around 7.5 million records right now. So it's a large data set. And here, let's see what the shape of this is again. 7.5, and let's see how much this is. So this is just 237 rows in there. So the next after this, we'll add another table to this. So df is equal to df dot merge, and this time we'll use the branded food. So branded underscore food, and let's check the shape of that. Oh, my mistake. And this has around 500,000 records. So let's get first couple of rows, and this has the FDC ID. We have FDC ID here, so we can join on that. And also we want to remember that if there are more than two columns common in both the data frames, I want to check if those two columns need to be used as a ID while doing the join. In this case, we just have one, so we'll use that. Branded underscore food on is equal to, this is going to FDC underscore ID. How is equal to, this is going to be inner again. And now let's check the shape. So let me copy this. We might lose some records, or it depends how many IDs match from the two tables. So first we had 7.5 million. Now we have 6.3. So we lost some records there. After this, what we are going to do is we are going to call the function that we created above, which is this one, to remove any data frames that have several null values. So the reason why I'm saying that is, let's say if we check the df.isNan.sum, so if you check the data frame for the null values, you see that this column has 6.3 million null values. So we don't need that column. It has no information. And so similarly, these columns don't have any information in them, and this one. So we'll go ahead and delete those, and then pick the important columns that we need for regression. To do that, I will simply type df is equal to drop underscore nan underscore dupes underscore calls df, and we'll set a threshold of 50,000 records. So if they are more than that or equal to that, we'll delete those columns. So again, we can check the shape, print df.shape, and let's see what we get. So we have only 16 records now. So we started with 16, and then we had 28 columns, and we'll get the final count for the number of columns after this. And while this is running, we can then check one FDC ID and see how that information looks on this site. So this is FDC ID 34. Let's copy this. I tried couple of them. Some of them from the CSV files show up on the site, some of them don't. So let's see if this one shows up. FDC ID is equal to this, and let's say dot head. Okay, so that is there. And as you can see, if you look at the information here, so we have 5.2 grams of protein for this product, and here we can see protein is 5.2 grams, and that's the product. So that's how this information is laid out. Okay, so now we can go ahead and do the next step, which is removing the. So if we scroll down here, there is energy information. So if we look at this name, so we can look at the unique values for that. So df.name.unique. So these are different types of nutrient information that's in that data frame. And we are going to use all of this information to predict the calories. So for this product, ash is this much, fatty acids is this much, etc., etc., and so these would be the resultant calories in that product. And so to do that, what I'm trying to get at is there is energy in here. So if we look at energy, okay, so the energy is what we need to remove from this column and put it, because that's going to our predictor, that's going to be our y value, and the rest of the data frame will be our x. Before we do that, however, we need to check uh, if the energy is expressed in different units such as kilocalories, calories, or kilojoules. And to do that, we can pull the records for energy. So if we say df and df, and we df is the row value, it's not a column name, so we need to use column name, which is name is equal to, and here we specify energy, and so this will pull all the records that have uh, only energy as the name. Once we have that, we can then use unique on this. We can use unique for the name column, name, and if you type unique, then we can see that these are the names. So there's just energy, which is good. And then we can look at the units. So the units is in unit name, and then here what we can do is type unit name dot unique when we only have energy. So we see that there are two units used, kilocalories and kilojoules, and we can check how many of each are there in the data frame. So to do that, we'll do a group by. So that's the data frame, and here we can say dot group by, and then put that in there, and then we can do a count on the unit name, unit underscore name dot count. And as you can see, we have around 463,000 records that have kilocalories. It's just 9 records that have kilojoules. If the proportion was 50-50, I would have converted the kilojoules to kilocalories or vice versa and used all the records. But because these are just 9 records, and because this is a tutorial, it's not going to matter if we drop those 9. So I'm going to drop the 9 records here. So let's do that. And to remove those records, what we can write is remove underscore FD. So we'll pick the FDC IDs for those and then filter them out. So is equal to df unit underscore name is equal to small k capital J kilojoules, and then get the FDC ID. Once we have the FDC ID, then we can use that for filtering. So we'll create the data frame x is equal to df, and here we are going to do 2 filters. The first filter is going to be for the energy column. So df name, and here we're going to, let me pull the df dot head. So we need this column. So all the rows in that column except the one where it says energy. So this is not equal to energy. So that's the first one. And the second one is we don't need, so we need to put that tilde sign there, df fdc underscore id and dot is in. So it'll do opposite of that. So not is in. Remove underscore fdc underscore id. It'll do opposite to is in with this tilde there. Now once this is done, the columns that we need to pull are fdc underscore id. Then we need the amount, because that's the one that has the values in there. And we need name, and I don't think we need the unit name. So unit name is gram. We could use it to convert them to uh, binary variables, so gram or different units. But for this exercise, we'll drop that. We won't use it. And then drop duplicates, because after we drop these uh, columns that are here, I'm sure there could be some of these rows which should have the same values. So this will take care of that when we drop the duplicates. And the same with this, we can create y, which is going to be uh, such that it will have only those rows which have energy as the name. And then we skip all these FDC IDs and we drop the duplicates. Rest everything stays the same. We run this, and then we can check the shape. So print x dot shape, x dot head, and look at the 2 records. So we now have around 5.8 million records, still plenty. And we check the shape of y and look at y dot head, and we have less number of records, and that is okay. Next, what we'll try to do is we are going to do the pivot. So convert rows to columns using pivot table. And if you remember from the beginner series, we pivot rows into columns. We use pd.pivot table, pd.pivot underscore table, and then here we specify the data frame and values that we want to pivot. So in this case, we just have the amount that we have, and then we'll use the index, and the index is going to be the FDC ID, and then we have the columns. Columns, we just have the one column name, and when we look at X head, we see that we should see the data frame which has all the values or the names as column names. So now we have all these nutrient information as column names and the values within for each nutrient listed in these rows right here, and each FDCID now represents a product. So what we can say is that each of these rows represent a product, and we are going to predict the calorie content of each of those products by using just these values for the nutrition. So if you happen to find, so the usage of the machine learning algorithm would be that you create an app where somebody could punch in the nutrition value for any product that's in a supermarket, and then this will give predicted values. Or if they are in lab, you punch this number in and you get the calorie content. Or if you are mixing and mixing or matching different products, this could help, or a variation of this could help. Now let's also check the shape of x dot shape, and we have around 483,000 records in here, and out of those, let's find out how many are NaNs. Is na dot sum, and we have massive number. We have 483,000 that are NaNs. Wow. And what is the shape again? X dot shape 83. So for some columns, almost all the records are 0 NaN. So we definitely don't want any of those records. So we'll run the function that we created above. So let me go ahead and add that here, which is x is equal to drop underscore NaN underscore duplicates columns x, and it will set the threshold to 50,000. And if there are still some NNs missing, we'll take care of those when we perform the outlier detection. So we also need to rename these columns because they are multi-level. We'll stack them and put them as just one level. And what I mean by that is, if you look at x dot columns and you look at the first one, these are tuples, multi-level tuples for amount, which is a amount common to all of them, and then there is this second level, which is this nutrient name there. What we can do is just use this second part and put that as a column name. To do that, I'll use for loop x in x dot columns. What we want to do is just take the first part, and that should fix all the column names. Now if we print x dot shape, after removing the columns, we'll have lesser number of columns in there, and we can look at x dot head and run this. So there's a key error. Let's find out why. The name is not there. So columns, let's look at what the x is. X dot head, and here we have, okay, the reason is because I ran this earlier. So let's run this, and that should fix it. We should have a nice data frame with FDC ID as indices for row, and the nutrient information as individual columns. with all the values within it. So this is a nice data frame. And as you can see, we ended up with just 8 columns. So we have carbohydrates, fatty acids, uh, saturated trans fat, fiber, protein, sodium, and sugars and lipids. So this example, we don't have uh, all the nutrients, but you can modify this particular code to such that it will have all the information. If the missing information is not there, or if you are able to get the missing information or impute it some way, then you'll have more features in here. But for now, we'll work with just 8 features. And let's now merge the y values in here. So we'll have each of these FDCID, each of these products aligned with their corresponding caloric value. So to do that, we'll use the merge in pandas. So x is equal to x dot merge, and we are going to merge with y, and from y we just need FDCID and the amount, and we are going to merge it. And recognize I've put 2 square brackets, and because we are going to use that as a data frame. FDC underscore ID how is equal to inner, and then so when we run this x dot head, so these as you can see, we have the amount information there now for each of the products. And I'm going this also would have x dot fill x dot is na dot sum, and this still has plenty of NNs. So in this case, I'm going to fill those with zeros. X dot fill NA with zeros, and then X is equal to. Now with this, we are now ready to split these such that once we have these aligned, we can split them and have them X separate and Y separate. We'll leave it this as is for now and proceed to the next step, which is removing outliers. Remove outliers, and to do that we'll use the quantiles. So we'll quantile, so we q1 is equal to x dot quantile 0.25, and then q3 is equal to x dot quantile 0.75. And so with this we can create a filter. So the filter 1 is going to be that x is less than the q1 minus 1.5 into interquartile range, and then the filter 2 is going to be equal to x is greater than q3 minus plus 1.5 into interquartile range, and we can plug this in here. So x is equal to x, and so not filter 1 or filter 2, and then we put, so this is going to be in parenthesis, and we specify any axis is equal to 1, and then print the shape of x. And so we have 10 features right now, and the reason is because this FDCID got converted to a column because we use that in the merge. If we look at x dot head now, left two additional columns. One is the amount and the other is the FDC ID. So with that, I think we are now ready to split this particular data frame in our standard X and Y format that we use for train test split. Let's do that. Separate, aligned X and Y. So here the Y is going to be X, which is just the amount column, and I'm going to use a copy. And then for X, it's going to be all the columns except the FDC ID and the amount. So X dot columns dot is in FDC underscore ID and amount. We don't need this, so we need to put a tilde in there, and this is going to create a mask that we can pass to X dot columns, and those are the columns that we'll be using from X. So now if we print X dot shape and print X dot columns, so we have carbohydrates, fatty acids, again second trans fat, fiber, protein, sodium, sugars, and total lipid fat. So these are the only features we have that we can use to predict the calorie content of a product. Very few features, and we'll see how that works. Next item is preprocessing. So let's do that. So what we have done so far is could also be called as preprocessing. Putting a title here. Now we'll first remove the steps in this way. This part would be similar to what we have seen in previous two projects. Variables with zero variability, and so what we need to do is find the variability for each column and then remove if it is zero. So if it's the same value throughout the column, we get rid of that column. X, and so here we say X dot var axis is equal to 0, and if that's greater than 0 we are good, else we don't need that column. Values, print X dot shape, X dot head, and so we have around 190,000 columns in there. For collinearity, we could also create a pair plot. So SNS dot pair plot X, and that will generate the plot. Alternatively, a much easier way is to create a heat map. So once this is done, we can plot the heat map as well. So why don't we add a heading here? Collinearity check. And so as you can see, the data is everywhere, and I don't see anything is correlated. Maybe some trend here, but not a straight line type of thing. So if we try to plot the heat map, it would look like this. So plt dot figure, and then fig size is equal to 5 by 3, and x underscore corr is equal to x dot corr. Take a square of that and plot sns dot heat map x underscore corr. The map is equal to where it is, and as you can see there are no yellow squares except along the diagonal, so we are good. Then we could also do transform, but I'll skip that here. We'll just use standard scaling. Standard So we'll standardize the data set, and so scaling SCL is equal to preprocessing dot standard scalar, and SCL dot fit x, and then we can look at x is equal to SCL dot transform x, and finally you can print the shape of x and the one of the values. So let's look at index 0 and has not attribute transform, so my mistake there. Okay, so those are the values, and now we have the data set x ready for creating the split and models. So we'll take a short break here and come back in part 3. Welcome back. In part 3, we are now going to begin with the modeling part. So that part 3, and the first item is splitting the data. So train, test, split. Probably recognized by now that I'm not doing the validation part here, not for these tutorials, but I'll add that in future videos. Y underscore test train, and then we have train, test, split, and x, y, shuffle is equal to true, and we just look at the shapes, x underscore train dot shape, and then x underscore test dot shape. So we have around 140,000 records for 45,000 records for train, and around 50,000 for the test. Now for modeling, it's the same approach that we have done in previous video, where we create a list and stack all the models in there and run a loop over that to get the output, and we'll create the same function. We'll use the exact same function from previous video, with minor modification. We change the name of the variable to reg instead of clf, because we are dealing with regression problem and not classification. However, it wouldn't make a difference if we use the same variable. Y underscore pred is equal to reg dot predict, and this would be on the test. And the changes are here for metrics. So we are going to use MSE, mean squared error. So metrics dot mean underscore squared underscore error, and this would be based on the y test and y pred. In addition to, so let's print this. So MSE is equal to this, and percent sign dot 4f, and again percent MSE. The next one we'll look at the R2 score. So is equal to R2 is equal to matrix dot R2 underscore score, again y underscore test, y underscore pred, and we can print the score as well, which is R2 score. And this again we specify percent dot 4f, and here we specify percent R2 R2. So that's the MSC and R2. Now we do not have a confusion matrix, but we can still visualize the result by creating a scatter plot of y test and y pred. If it's a good prediction, then both the values of y test and y pred would be similar, and so when we look at the scatter plot, it would be a kind of a diagonal uh, array of scatter points in the xy plane. And can plt.show, so we can see that for each iteration. And we can return. So I think, yeah, so we are printing the value and then we can return both the MSE and the R2 values. So that's the function. Now for a model, we'll create a model list same as before. We put the tuples in here. So linear underscore model. I'm going to copy that because we'll be typing that several times. Linear regression, open close parenthesis, comma, linear regression is the first one. And the next one we have ridge. And again, this is going to be ridge regression. And then we have the next one. So this is going to be ridge CV, and again the name for that RidgeCV. So this we have Lasso, and let's set the alpha value of this to 0.1, and this is going to be Lasso regression. And then for this we have Lasso, we have Lars, so least angle regression, LARS. And again for this we'll use the n non-zero underscore coefficients. The value of that we'll set it to 2. And we have least angle regression, or LARS. And after this we have LassoLars. So LassoLars, and again here we can set the alpha value to 0.01, and we can look at, I give it this name, LassoLars. After this we have ElasticNet, and we can set the random underscore state is equal to 0. And we have ElasticNet regression. And finally we have the same ElasticNet but with cross validation. So ElasticNetCV, and we can use CV cross 5-fold cross validation. Random underscore state is equal to 0, and the name again is going to be ElasticNetCV regression. So that's the list we have, and we can initialize a list to save the result as results. Let's put an S there, and after this we can run the for loop. So for reg name in model underscore list, we can print some lines there to separate the output, and that's there. We can print the name, and then again print the same output line. So let me copy that. So we can print that line, and here we now have results dot append. We have in here we have fit underscore predict, and we have reg, and then in the same tuple we have the name there, so those will get stored. And finally we run this print there. So the values within each of these models, uh, you could change the values, see what results you get. You could also pull each of these regressors separate, run it with different parameters, do a separate cross validation on that, and see if you can improve the score. You improve the R2 score or decrease the MSE, and you see if how the MSE compares between these models, which model gives you the least MSE and the highest R2 score. So let's run this, and we have error. So of course I made a mistake. Ridge. Okay, so here we have fairly high R2 score. We have 1247, and we have a coefficient 95, R square value of 0.95. So all of these look like they are same 95. So this is 88.89, that's fairly low, and that is for least angle regression. And here these we have 95, 94. So let's see what we can do to see if we can improve this little more. So here what I found is the y values that we have. So if we look at the y's, uh, some of, so let's say type y, we have the series, so y. Now if we look at the y values that are equal to 0, so there are y values that are equal to 0. We count those, there are 2000 y values that are equal to 0. So if we remove those records, maybe it'll improve the accuracy, because those 0 values for calories are not helping. And to do that, we could go back up and could add a line somewhere here. Here you could say x is equal to x, and for the amount column, do we have the amount column x? So let me go back up here from this part. So we create the x again, so that's there. Then we have we create the pivot table there, so we can run that column. And now here we can add amount, and that is not equal to 0. So once this runs, we'll see this. We have x dot merge y. So once we merge with y, we have the amount column in there, and we add this filter to remove the rows or records that have the value set to 0 for calories. Now if we run this all over again, see if it makes any difference, and run this and delete this last cell. So uh, here, as we have seen while this is running, I just want to talk that this dataset is rich with information, and if you have the time and interest, you could create new tables, new data frames, and run classification regression tasks based on the data that's available. So as you can see, the R square value jumped to 97, and the MEC dropped to by half. So the MEC was around 1200, I think, earlier. Now we dropped to 650. So that's the linear regression. We have ridge regression here, and all of them are around 650. Lasso, and surprisingly, the values are pretty close. Then we have Lasso. Least angle now is at 91. Maybe for Lars, least angle regression, if you increase this to maybe 5, maybe that will change things. We have that. Lasso, Lars. So now it's come down to 63. We have 0.97 for our least angle. And then same LassoLars is there. The ElasticNet is 0.90, but you could improve that by setting the parameters. So ElasticNetCV is much higher. It's at 0.96. So that was it for this video. I hope in this project you learned how to perform uh, regression modeling on a real world data set, and get predictions for the values. So in previous video we did classification task, and this was the food data. which where we use the nutritional values for products. These were branded products uh, that are used, and then we try to predict the calories for that. Here there are also data sets for foundation foods, so this could be kale or apple, and you'll have the nutrition value for that and also calorie content for each of those. So you could try working those data sets, working on those data sets as well. This value goes up, the maximum is 1. If you can take it to 0. 0.8, 0.98, 0.99, that will be more accurate. And if this could go down further, 0 is not possible, but if you can maybe half that to 300, that would be another improvement in the regression model. So I hope to see you all in next video. Please like, share, and subscribe. If you have any comments or suggestions, please let me in the comment section below. Thank you.